On July 1st, 2015, Mars 1 released to the public its first conceptual design study. Created by the Paragon Space Development Corporation, it outlines the initial architecture for an environment control and life support system which could be used for a human outpost on Mars. Now, in this video, I'm going to explain the key functions of the life support system and how they all work. I'm going to summarise how the outpost would work both before and after the first crew arrives, and finally examine some of the key issues identified in the report that will need to be followed up in future studies. The Environmental Control and Life Support System, also known as the ECLSS, is one of the most vital parts to enable a human presence on Mars one day. This video is based on the 52-page report issued by Paragon, but if you're after a quick summary, myself and two of the other Mars 1 Round 3 candidates have recently compiled a 2-page abstract which contains all of the most relevant technical data in a concise format for the technically minded. I also note that a great place to start the report if you're looking for a detailed breakdown, perhaps say for modelling purposes as a student project, is page 42 onwards. You'll find links to both the full report and our abstract down in the description. First, a little bit of background. So, according to Mars 1's mission architecture, 2 ECLSS modules are to land in 2025, where they will have to operate autonomously with just rover assistance for the first 2 years of their operational lifetime. During this period, they will have to collect and store a minimum required amount of both water and oxygen, and also achieve full pressurization of 2 surface habitat modules before the first crew would be allowed to depart in 2026. After the crew arrives 7 months later in 2027, there would be a period of a few weeks before additional landings would take place, including 2 further ECLSS modules. Now, during the initial phase, when there are just 2 ECLSS modules on Mars, in case both of the modules fail, between them enough life support consumables are stored for 30 days of operation. An example of what might cause a failure of both modules would say be insufficient electrical power provided, which could indeed happen during a global dust storm, for instance. However, if one module were to become completely non-functional, then long-term contingency operations can be entered into for a period of up to 2 years until the next resupply shipment arrives, which can sustain a crew of 4 on Mars. Okay, so now let's take a look at how an ECLSS module actually works. So it's divided into 5 major subsystems, each of which I'll examine in turn. In Situ resource processing, water management, atmosphere management, thermal control, and finally wet waste processing. Firstly, let's take a look at in situ resource processing, which is all about using local resources present on Mars in order to reduce the need for them to be supplied from the Earth. The first function of this subsystem is to collect water from the Martian environment. This is done by loading regolith, meaning Martian surface material, into a container, or hopper, which is then heated to vaporize the ice contained within. The resulting water vapour is then condensed, accumulated, and then transferred to the water management system to be purified. The second function is nitrogen and argon extraction from the Martian atmosphere. To do this, you first need to remove the dust and other small particles from the collected Martian air, but then once you've done that, you need to also remove the carbon dioxide, which makes up around 95% of Mars's atmosphere. To do this, you first compress the incoming gas to multiple atmospheres in pressure. Now remember that when you compress a gas, it releases heat. Now this heat can actually nominally be used for the aforementioned water vaporization, so it's very efficient actually. But after compression, the gas can then be rapidly expanded through a throttle valve, which results in cooling through something called the Joule-Thomson effect. This is much in the same way as how refrigerators work actually. So at this point, the carbon dioxide present in the air becomes liquid or solid because it's been cooled down substantially, so the carbon dioxide simply drops out of the gas, leaving behind the desired mixture of nitrogen and argon. The carbon dioxide can then be either stored for potential use as a compressed gas, say to remove dust from equipment, or indeed simply vented outside of the habitat. Now, any water that you collect from the Martian environment, or say from humidity condensation, will not be immediately drinkable. So for this, you send the water to the water management system for purification purposes. Initially, the wastewater is pumped from a storage tank through a particulate filtration bed, which removes particulate contaminants, an activated carbon bed, which removes most of the organic contaminants, and an ion exchange bed, which removes inorganic contaminants, such as, say, heavy metals. Now, you need to also remove the remaining organic contaminants. To do this, you pass the water through an aqueous phase catalytic reactor, which oxidizes these organic compounds, converting them into carbon dioxide, water, and other harmless byproducts. Any residual contaminants at this point in the form of vapours can then be vented before the water passes through a final ion exchange bed, which will remove the byproducts from the oxidation process. After this quite extensive process, the electrical conductivity of the water is then measured and compared with that of pure water to check for purity. If it fails the purity standard, it's then redirected back to the wastewater storage tank after passing through 2 ultraviolet disinfectant lamps, which are used in order to kill any microbes present in the water to prevent contamination of the tank. However, some of the water, of course, will be pure. The water which has been approved as being pure can then be used for drinking, food production, hygiene, oxygen production, or transferred to an internal or external storage tank. Now on to perhaps the most important subsystem, the atmosphere management system. First up, high pressure drinkable water with a pressure of say around 68 atmospheres is fed into an electrolytic reactor. This uses the chemical process of electrolysis, whereby an electrical current is used to break down water into hydrogen and oxygen. The hydrogen is then vented outside the habitat, whilst the oxygen is mixed in with the airstream or stored under high pressure. Contained within the atmosphere management system, you can also see the atmosphere revitalization subsystem down at the bottom, which is responsible for maintaining the quality of the air. Let's take a look at how it works. So firstly, the air passes through high efficiency particulate arrestance filters covering an air inlay, which removes 99.97% of particulate matter greater than 0.3 microns in diameter from the flow. Fans drive the air through a trace contaminant control assembly, which uses activated carbon and high temperature catalytic oxidation to remove any airborne inorganic and organic contaminants generated by the crew, very much analogous to the purification process carried out on the water supply. Next up, you need to consider what you do if, say, there has been a fire, you've already extinguished the fire, but you need to be able to remove the harmful products of the combustion process. So what you do here is a cartridge is inserted into the airstream, which removes organic compounds and also crucially converts carbon monoxide, a key byproduct of a fire, into carbon dioxide. The carbon dioxide can then be removed using a very clever device called a 4-bed molecular sieve. Basically, this works by passing the air over a desiccant bed, which causes water to stick to it and then release heat. This results in dry, hot air containing carbon dioxide, which you can then pass over another bed containing zeolite, a material which contains holes at just the right size that it preferentially causes carbon dioxide molecules to stick to its surface, thus removing it from the airflow. The warm, dry air then passes over a different bed that's already saturated with water, which allows it to recollect the water and return to the habitat's airflow with CO2 no longer present in the air. But once the zeolite bed is completely full of carbon dioxide, the flow can then switch over to a second, now dry water collection bed, and also a second zeolite bed free of carbon dioxide, hence the name a 4-bed molecular sieve. The first zeolite bed can then be heated in order to drive off the carbon dioxide, which is then transported via a vacuum pump to an external vent or simply into storage. The process is thus continuous, alternating between the 2 pairs of beds. Very fancy. It's also worth noting that the atmosphere management system is responsible for monitoring the overall air quality inside of the habitat. It does this by measuring the concentrations of oxygen, nitrogen, argon, carbon monoxide, carbon dioxide, hydrogen and water vapour present in the atmosphere inside the habitats using a mass spectrometer. Now you also need to have a handle on the absolute pressure inside the habitat, which is done using some pressure transducers which continually update and inform the master control computer within the habitat to let it know what's going on. The master computer can then autonomously, or indeed the crew can actually manually control the release of various valves which can introduce more oxygen, nitrogen or argon into the atmosphere selectively, or indeed if you have an overpressure situation, vent to the external environment to prevent the overpressure from developing way beyond control. But of course, being able to breathe is all well and all good, but it doesn't help if you freeze to death. But luckily that is where the thermal control system comes into play. The thermal control system is responsible for maintaining the temperature of the habitat within a comfortable range of 18 to 27 degrees Celsius. To do this, there's a balance you need to strike, because on the one hand, you need insulation to stay warm against the external Martian temperature environment, which averages around minus 58 degrees Celsius, but you also need to be able to reject the heat generated by the crew and the equipment inside of the habitat, otherwise you will overheat. The thermal control system handles this using electrical resistance heating to generate heat, just simply using Ohm's law. It uses both also air convection and liquid cooling loops in order to transport heat from location to location, and finally external radiators to dump any additional heat which you have that you need to get rid of into the external Martian environment. Finally, the wet waste processing system stores wet human waste, things such as, for instance, urine, feces, and also waste associated with food and hygiene behind a humidity exchange membrane. Dry air is passed across one side of the membrane, which recovers water released by the waste upon heating. The resultant waste, or sludge, is then stored with an eye to eventually be used as a source of organic and inorganic compounds with additional recycling capabilities in the future. Right, so now we know how an ECLSS module works. Let's take a look at the requirements Paragon has identified for each module, both before and even after the first crew arrives on Mars. So first up, you need to produce a lot of life support consumables locally on Mars before the first crew arrives. Indeed, during the first 365 days of operation, first up you need to produce oxygen. This is produced at an average rate of around 1 kilogram per day, of which 120 kilograms is used in order to complete one full pressurization of each 500 cubic meter habitat, with also 120 kilograms going into storage as pure oxygen, and a final 120 kilograms being mixed in with both nitrogen and argon to create a contingency buffer which can be used in order to complete one full inflation of the habitat in case, say, that we go into contingency operations and we need to just vent everything out, which is not pleasant of course, but you have to plan for contingencies like this. Nitrogen and argon, on the other hand, are produced at the slightly higher rate of 1.8 kilograms per day, which allows 320 kilograms to go into storage for the contingency buffer, and also 320 kilograms to be used to complete one full pressurization of the 500 cubic meter habitat. Right, you also need water, of course, incredibly important. So 5.9 kilograms per day of water is produced, which enables 1,500 kilograms to go into storage, with the additional water being used to produce oxygen via electrolysis. So what are other things you need to know? Well, the pressure inside of the habitat is maintained at around 69% of 1 Earth standard atmospheric pressure at sea level, of which a maximum upper limit is put into place of 0.5% of an atmosphere for the partial pressure of carbon dioxide, which is a quite standard requirement from space agencies. You also need to consider what the temperature range is going to be. Now, it falls slightly outside of human comfort range before the humans arrive. It's maintained between 12 and 37 degrees Celsius. The lower limit of 12 Celsius is designed in order to stop condensation from occurring on cool surfaces, while the upper limit is pretty much there in order to reduce the energy requirement from active cooling systems. Okay, so it's 2027. The first crew has arrived. Now, crucially, it's time to significantly step up the ECLSS operations. First up, you need to ensure that there is a habitable mixture of gas, and in this case you have 25 to 30% oxygen by composition in the air, with the other 70 to 75% being made up of a mixture of nitrogen and argon. This is of course higher than the average oxygen concentration at sea level on the Earth, which hovers at around 21%, but the reason for this is that the crucial parameter that determines how your body responds to oxygen is something called the oxygen partial pressure. And because the total pressure inside the habitat is lower, hovering at around, say, 70% of an Earth atmosphere, you need to compensate for this by increasing the concentration of oxygen molecules inside the habitat. So the other requirements are summarised in this table, but there's a few that I'd like to take note and elaborate on a little. So firstly, with regards to the in situ resource utilisation, oxygen is produced at a higher rate after the first crew arrives of 6 kilograms per day by each module. The breakdown of this is 3.56 kilograms per day for the crew metabolism for your first crew of 4, 0.57 kilograms per day due to leaks from having just imperfect closure of your habitat, and 0.91 kilograms per day from losses due to cycling of the airlock when you go outside wearing your Mars pressure suit. There's also then an additional margin added to make up for, say, if you want to replenish any of the oxygen stores. This is what makes up the 6 kilograms per day. It's similar for the nitrogen and argon, which are produced at the rate of 7 kilograms per day, but in this case, only 1.53 kilograms per day need to be replaced due to leaks, and 2.44 kilograms per day due to airlock cycling, so there's actually quite a significant margin here. Particulate matter is also a concern. You don't want these contaminants floating in your air supply. So any matter in the size range of 0.5 to 100 microns must be restricted to a concentration of less than 0.2 milligrams per cubic meter, otherwise you're going to suffer from respiratory system irritation when you breathe in. The temperature range is also much more constrained than as opposed to, say, before you arrived, held at between 18 to 27 degrees Celsius to enable human comfort. 62 kilograms per day of drinkable water are produced, of which 53 kilograms per day is recycled, which is collected as condensate on the heat exchangers, and 9 kilograms per day is extracted from Martian regolith. This assumes an 84% in situ resource utilisation water recovery rate. Now, for the purposes of the analysis of the in situ resource utilisation, it was assumed that the Martian regolith contained a water content of 5%, which is quite typical of the 40 to 45 degree north landing latitude that Mars 1 is considering. And this would require 198 kilograms per day of Martian regolith to be fed into the ECLSS modules. Finally, a maximum of 940 kilowatt hours of heat must be collected and rejected each day, which assumes a 75% electrical to thermal conversion rate on the longest day of the Martian year. Putting all of these requirements together, Paragon has designed an ECLSS module with the following physical characteristics. The key takeaways from this table are that the total mass of each module is 7,434 kilograms, the total volume is around 20 cubic meters, and the minimum energy required per day of operations is 392 kilowatt hours once you factor in a 10% margin of error. Also, the in situ resource utilisation needs to run for around 8 hours per day. So each of these modules on average needs to take only 1 hour in order to repair it once it goes down for contingency operations, and it also needs to have a minimum operational lifetime of 10 years, ideally higher than that. It's also noted in the report that even at this stage it's envisioned that many of the components of the ECLSS module will be compatible with 3D printing, which could enable local additive manufacturing to be used for replacement part strategies. Okay, so to wrap up, let's quickly examine a number of the key issues that Paragon has identified at the end of the report, and some potential areas for improvement in future designs of the ECLSS system. So the thing that really stood out to me is the mass of the module, which is estimated at around 7.5 tonnes. So Paragon notes that during this initial conceptual design study, they didn't put any hard upper limits on the mass of the design because they favoured simplicity above everything else. But they also note that the mass can be brought down. It will just drive up development costs as they have to seek more lengthy and more costly ways in order to increase efficiencies. But crucially, it could be done. So what you need to do in this case is, firstly, Mars One needs to know what is the upper mass that they can actually land on Mars. They've previously been estimating around 2.5 tons, but they need to consult with the primary landing partner, which at the moment is Lockheed Martin, to establish a firm number on what can be landed on Mars. This number can then be passed on to Paragon, which will then be used as an hard upper mass limit for any future iteration of the ECLSS module. Another issue is the regolith supply mechanism, which requires around 198 kilograms per day of Martian regolith to be loaded into an ECLSS module and also removed after the water has been extracted from it. This will require a separate conceptual design study to outline precisely the mechanism by which this will be achieved. Thirdly, electrical energy generation on the shortest day of the Martian year is estimated at 267 kilowatt hours per day, which is less than the estimated 392 kilowatt hours per day that an ECLSS module requires to be operational. So there are a number of ways that you could deal with this. I mean, the obvious way, just have more solar panels, but you could also say have more storage of key gases such that you produce more of them during the longer days of the Martian year when you have more electrical power available from solar energy, and then just store it for later use. But an even simpler way would just be to drive efficiency with the in situ resource utilization, because that's where most electricity is required. So any savings you can make via the things I've mentioned earlier, say for instance not losing as much gas each time you cycle the airlock, can drive down the amount of resource you need to produce locally, and by extension the amount of energy you need substantially. So that could certainly fix this problem in this case. Fourthly, Paragon notes that if you were to store the hydrogen produced by electrolysis instead of venting it to the Martian atmosphere, you could actually use it as an input to the Sabatier process one day in order to convert carbon dioxide into water, providing an excellent alternative source of water to extracting from Martian regolith. Fifth and finally, Mars One eventually plans to grow crops locally on Mars to be used as food for the colonists. Now, this means that the plants themselves are obviously producing oxygen, they're also taking in carbon dioxide, and this is going to affect the balance of gases in the atmosphere. In future studies, you need to make sure that this is not going to affect the operations of the ECLSS module. This is called the effects of bioregenerative life support, as opposed to the physiochemical life support that the ECLSS module designed by Paragon uses, which doesn't use any plants whatsoever, hence the physiochemical, physical and chemical processes only. Of course, it's really nice that the ECLSS module does work independent of plants, but we just have to be careful to make sure that the plants aren't going to eventually mess up the module one day. So again, it's worth stressing that this is only an initial conceptual design study. Doubtlessly, the various parameters I've mentioned and also the intricacies of the design will have to change over time, but even at this stage, I'm really encouraged by what we're seeing. I think it's a great step along the direction to enabling a human settlement on Mars, and if anything, it's my sincerest hope that this study will help us bring us one step closer to the day when we can look up at the stars and proudly proclaim ourselves as a multiplanetary species. Thanks for watching. Can you think of any solutions to the issues I've pointed out? Or perhaps do you have some further questions about Martian life support? Let me know in the comments down below. This week's featured video is the 2007 documentary The Mars Underground, focusing on Dr. Robert Zubrin's Mars Direct plan, which is advocated quite strongly by the Mars Society. Next up, I'll be sitting down with Australian Mars One candidate Diane McGrath to have a conversation about our shared experiences from being involved with the project. Be sure to subscribe so you don't miss it.